This is section 4.3, Eigenvalues of Special Matrices. What's going to happen in this section is we're going to get a characteristic polynomial that isn't going to factor so pretty like it did in that last section. So we're going to see how to handle that and what might happen when we get to that point. Section 4.3, Eigenvalues of Special Matrices. All right, first of all, what if they asked us to find the eigenvalues of this 2 by 2 matrix, and the matrix contains 1, 4 in the first row, 2, 1 in the second row? All right, well, you remember how I do this is I set the determinant of a minus lambda I equal to 0. So first of all, I found a minus lambda I. Now, I, again, is just the identity matrix of an appropriate size. In this case, we'd want to use a 2 by 2 identity matrix, since I have a 2 by 2a. All right, so I would get, just skipping all the steps in between, 1 minus lambda, 4 in the first row. Then the second row would be 2, and then 1 minus lambda. And like we saw in the last section, what essentially happens is you get minus lambda attached to all the entries in the main diagonal. Okay, now set that determinant equal to 0. Okay, to do the determinant of a 2 by 2, if you remember, it's the entries in the main diagonal, which are 1 minus lambda and 1 minus lambda, multiplied together, and then minus the other diagonal. Okay, so I get 1 minus lambda times 1 minus lambda minus 2 times 4, so minus 8. All right, then working that out, doing a little bit of algebra, I get 1 minus 2 lambda plus lambda squared minus 8 is equal to 0. Putting it in an order where I can kind of deal with it, I have lambda squared minus 2 lambda minus 7 equal to 0. Okay, like we said, in this section you're going to get polynomials that don't factor. This is one of those polynomials. It doesn't factor pretty for us. So remember your old buddy, the quadratic formula? Well, you're going to have to use it in this section. The quadratic formula works like negative b plus or minus square root of b squared minus 4ac, that quantity, over 2a. Now the a, the b, and the c are the coefficients in that order of the lambda squared, the lambda, and then the constant term. So the c is actually the constant term. So when I plug in the negative b for this one, I'm actually plugging in a positive 2. And then plus minus square root of, okay, negative 2 squared is 4, minus 4 times a is 1 and c is negative 7. All of that's over 2a, and since a is 1, that's just 2. All right, now 4 minus negative 28 is 4 plus 28, which is 32. So I have 2 plus and minus the square root of 32 over 2. And then obviously 2 over 2 is 1, but then I still have the 2 underneath the square root of 32. The square root of 32, since that's 16 times 2, and 16 is a perfect square, the 4 comes out. 4 root 2 over 2, and then the 4 and the 2 cancel, and I end up with 1 plus and minus 2 root 2 as my eigenvalues. Okay, not too bad once you get into it. Can be a little scary, though, if you didn't remember the quadratic formula. Okay, matrices with real number entries may have complex eigenvalues. Now in that one we saw we just had a square root of 2 in our lambda values. But it is possible that we would actually have the square root of a negative number. Okay, for example, find the eigenvalues for a equal to 1, 2 in the first row, and then negative 2, 2 in the second row. It's a pretty normal looking matrix. You wouldn't think anything strange is about to happen. But watch, when we do a minus lambda I, we get 1 minus lambda, 2, and then negative 2, 2 minus lambda. So again, just the entries in the main diagonal get a minus lambda attached to them. Now, take that determinant, set it equal to 0. When you do the determinant, you get 1 minus lambda times 2 minus lambda minus negative 2, which winds up being plus 4, of course, minus negative 2 times 2, excuse me, which winds up being plus 4. Then working out the 1 minus lambda times 2 minus lambda, we get 2 minus 3 lambda plus lambda squared plus 4. And then rearranging that so that we have the lambda squared in front, we get lambda squared minus 3 lambda plus 6. Okay, now again, this is one that doesn't factor. If you try all the factors of 6, 1 and 6 and 2 and 3, I can't get anywhere with that. So I have to use the quadratic formula. This time I get 3 plus and minus the square root of this quantity. Negative 3 squared is 9. Then minus 4 times a is 1, c is 6. All of that mess is over 2. All right, now simplifying what's underneath the square root, I have 9 minus 4 times 6, which gives me a negative 15, because 9 minus 24, negative 15. Okay, now I have the square root of a negative number. That's going to give me an imaginary number. When you have the square root of negative 1, we call that I. Now, we're not going to do a whole lot with imaginary numbers in this class, but you do need to be familiar with the concept of the square root of negative 1 being I. So when you have something like the square root of negative 15, you are expected to be able to change that to say I times the square root of positive 15. Okay, because the square root of negative 15 is the square root of negative 1 times the square root of positive 15. So since the square root of negative 1 is I, then I just make that substitution. Okay, that's about as complicated as imaginary numbers are going to get in this class. But you do need to be familiar with them. And of course, you'll use them a lot in future classes, like vector geometry and differential equations. Anything with an I in it is called a complex number. Complex numbers are of the form a plus bi. The a is the real part, so that's just going to be like a regular number, like a 3 or a 2 or something like that. And the bi is the imaginary part. Okay, a complex number is in the form a plus bi. And a lot of the questions, especially if you're doing the ones on the computer, are going to say blank plus blank I, and you have to fill in the 2 blanks. Okay, for a real matrix, complex eigenvalues always occur in conjugate pairs. That is, if a plus bi is an eigenvalue, then so is a minus bi. The reason this happens is because those eigenvalues, those complex eigenvalues, always come from the quadratic formula. And because the quadratic formula has a plus minus in it, right in front of the square root, that's going to mean that I have a plus minus bi every single time. So anytime I have something in the form like 2 plus 3i as an eigenvalue, then I also would have 2 minus 3i as an eigenvalue. So conjugate pairs. Let's look at this example. Which of the following could be the eigenvalues for a 3 by 3 matrix? Now the significance of my saying 3 by 3 matrix is, if you remember in the last section, it said the maximum number of eigenvalues that I can have for an n by n matrix is n. So the maximum number that I can have here is 3. So these aren't going to be partial lists if I have 3 numbers. For example, I have 3i and negative 2. Then I also have negative 1, 1, and 4 plus 3i. Now again, because this is a 3 by 3 matrix, this has to be a complete list because the most I can have is 3. All right, so choice 1 was the 3i and negative 2. Choice 2 is the negative 1, 1, and 4 plus 3i. Then I have negative 1, 2 minus I root 3, and 4 plus 3i. Then the fourth choice is negative 1, 2 minus I root 3, and 2 plus I root 3. Okay, going back to choice 1, I had 3i and negative 2. We just said that complex eigenvalues have to occur in conjugate pairs. Well, here I see an I, but I don't see a negative I. So that means that that first choice is gone. All right, now for the second choice, I had -1, 1, and 4 plus 3i. Again, I don't see a conjugate pair. I don't see the 4 minus 3i. And it's not like I could say, well, it's just that the other one is not showing. Well, because I already have 3 values showing, and that's the most I can have. So that one is also out. Similar situation in the third choice. I had 2 minus I root 3, but I didn't have 2 plus I root 3. I had 4 plus 3i, but I didn't have 4 minus 3i. So the conjugate pairs are not present for that one either. Then for the last one, I do see 3 values. You know, I could just have 2. That wouldn't be a big deal either. But then I have 2 minus I root 3, and I have 2 plus I root 3. So that's my conjugate pair that I was looking for. So that is my choice. All right, recall that a symmetric matrix is a matrix such that A is equal to A transpose. That was from section 2.9, if that doesn't seem familiar. For example, if you have A, which is 1, 2, 3, 4 in the second row, 2, 5, 6, 7 in the second row. I don't know if I said that right. First row is 1, 2, 3, 4. Second row, 2, 5, 6, 7. Third row, 3, 6, 8, 9. Fourth row, 4, 7, 9, 0. In that matrix, if I were to switch the rows and columns, which is how you find a transpose, since the first row is the first column, and the second row is the second column, and so on, that would be the same if I were to transpose it. I would get the exact same matrix over again. So that's a symmetric matrix. Now, here's why we care what a symmetric matrix is. A symmetric matrix with real entries has only real eigenvalues. So if I have a symmetric matrix and it has real numbers in the matrix, I'll never get a complex eigenvalue. Okay, we'll never get a complex eigenvalue from a symmetric matrix unless there are complex entries. Next, we need a definition. A triangular matrix. Sounds crazy, doesn't it? A triangular matrix is a square matrix whose entries either above and to the right of the main diagonal are zeros, or below and to the left of the main diagonal are zeros. Okay, so I have to start with a square matrix. Then I look at the main diagonal. If all the entries above and to the right, or all the entries below and to the left of that main diagonal are zeros, then it's called a triangular matrix. So a triangular matrix is a square matrix. Seems pretty strange, doesn't it? All right, here are some examples. The following matrices are triangular. In the first one, you see I have 1, 0, and then in the second row, -5, 13. Well, if I look at the main diagonal, the 1, 13, above and to the right of it is a 0. So that's called a triangular matrix. In future classes, you'll actually talk about upper triangular and lower triangular. We don't really get into that in this class, but that's coming. All right, and then the next one, I have -2, 4, 7 in the first row. The second row is 0, 5, -1, and the third is 0, 0, 6. Again, looking at the main diagonal, you'll see that below and to the left of the main diagonal are all zeros. So that also is triangular. All right, next I have a 4 by 4. Again, looking at the main diagonal, the 6, 2, 3, 0. Looking below and left of that main diagonal, all I see are zeros. So this also is a triangular matrix. And then the last example, again, looking at the main diagonal, the 4, 2, 17 is the main diagonal. Above and to the right of that main diagonal, all zeros. Now, it doesn't matter that there are some zeros below and left. That doesn't matter. All I'm concerned with is that either above and to the right or below and to the left. It doesn't have to be both, and it doesn't have to be that if above and right is zeros, then I can't have any zeros anywhere else. That's not the case at all. All right, you see in the 4 by 4, I even had a 0 in the main diagonal, but no problem there. All right, why do we care about triangular matrices? Because the eigenvalues of a triangular matrix are the entries on the main diagonal. Let that sink in. The entries on the main diagonal are the eigenvalues. So if I had this example, the 1, 0, negative 5, 13, and that was the first example on the last screen. If it asked me to find eigenvalues for it, since it's triangular, they're 1 and 13. I'm done with that problem. How quick was that? Okay, now before I showed you this theorem, this next example, the eigenvalues of the 4 by 4, which the first row is 6, 4, negative 1, 0, second row is 0, 2, 1, negative 2, third row is 0, 0, 3, 1, and last row is all zeros. To find the eigenvalues of that guy would be pretty complicated, pretty nasty. So it's probably a good thing that you know this theorem, because the eigenvalues are just 6, 2, 3, and 0. So that made it a really quick problem. Took all of, what, 12 seconds. Whereas before, we would have been working for probably a good 15 minutes on it. All right, the following statements are equivalent for a matrix. So if I have some matrix named A, the following three statements are equivalent. The first statement says lambda is equal to 0 is an eigenvalue for A. So I have one of my eigenvalues chosen to be 0 for A. If and only if the determinant of A is 0, and that's going to happen if and only if A is not invertible. Now you probably remember the second and third statements from some previous sections. That was where it said the determinant of A is equal to 0 if and only if A is not invertible. So that should seem familiar. But then the first statement, the lambda equals 0 is an eigenvalue, that's the new part of this. So we know that we have an eigenvalue of 0 if and only if the determinant is 0, or if we happen to know that the matrix is not invertible, then we know lambda equals 0 is an eigenvalue. All right, here's what that does for us. If you have an example that says for a 3 by 3 matrix A such that the determinant of A is 2, not 0, right? Which of the following could be the list of eigenvalues? All right, again, the significance of having a 3 by 3 means the most values that can be listed would be 3. The determinant of A equals 2 means the thing is invertible. A is invertible. So that told me from the previous theorem 0 could not be in the list. All right, let's see what they give me. 3i and negative I, 0, 4 minus 3i and 4 plus 3i, 0, 2 and 4 plus 3i. And then they give me 1, negative 1, 2 minus I root 3, and 2 plus I root 3. Okay, just look at that last one. The 1, negative 1, 2 minus I root 3, and 2 plus I root 3. Do you see anything wrong with that? Looks to me like there are 4 numbers listed. And we had a 3 by 3 matrix, so I can't have 4 eigenvalues. So immediately I can rule that one out. All right, then just kind of moving backwards, the 0, the 2, and 4 plus 3i. Even if you don't make any other connections there, 4 plus 3i can't be present without 4 minus 3i, because I have to have conjugate pairs, so I can throw that one out. Okay, the other significant piece of information was that the determinant of A was equal to 2. That means 0 can't be an eigenvalue. That's what that last theorem said. When it said the matrix would have a determinant of 0 if and only if lambda was equal to 0 as one of the eigenvalues. Okay, so that's like saying if the determinant isn't 0, lambda can't be 0. Okay, I can negate both of those statements. All right, that leaves me with 3i and negative I. There's nothing wrong with that. I do have the conjugate pair there. I don't have 0 listed, so that's my choice, 3i and negative I. All right, the matrices A and A transpose have the same characteristic polynomial and hence the same eigenvalues. Now, if you remember where the characteristic polynomial came from, when I find the determinant of A minus lambda I, now what the difference is between A and A transpose is that the rows become columns and columns become rows. But the nice thing is the entries in the main diagonal don't change. So when I go to find the determinant of A transpose minus lambda I get the same characteristic polynomial. So I'm going to get the same eigenvalues. However, they usually are going to have different eigenvectors. Okay, so same eigenvalues for A and A transpose, but different eigenvectors. All right, some other facts in this section. If lambda is an eigenvalue for the matrix A, then lambda to the n power is an eigenvalue for A to the n power. So for example, let's say that I have a particular matrix where 2 is an eigenvalue. If I were to then do A to the third power, then I know 2 to the third power would be an eigenvalue for the new matrix. All right, also, if lambda is an eigenvalue for the matrix A, and A is invertible, in other words, the determinant of A isn't 0, then lambda to the -1 power, in other words, the reciprocal of lambda, is an eigenvalue for A inverse. Okay, so going back to that other example, if I have a matrix A where 2 is an eigenvalue, then 1/2 would be an eigenvalue for A inverse. All right, and then if a matrix has complex eigenvalues, then it will have complex eigenvectors corresponding to those eigenvalues. Okay, so complex eigenvalues imply complex eigenvectors. Let's look at an illustration of that one. Coupled with that is an example where we find the eigenvalues of a 3×3 matrix. So I have a 3×3 matrix of 1, 0, -1 in the first row, 0, 2, 2 in the second row. Third row, 0, -1, 0. And I want to find eigenvalues. So just like all the other examples, I want to do A minus lambda I and take the determinant of it. Okay, so the determinant of A minus lambda I would be, now remember with the 3×3 you have to choose a row or a column. In this case I definitely want to go with column 1 because that gives me 1 minus lambda times, now if you mark out the first row and first column you get 2 minus lambda, 2, -1, and then negative lambda. Multiplying out the determinant of the 2×2, I have 1 minus lambda times, here's the 2×2 determinant, 2 minus lambda times negative lambda, then plus 2, because it would be minus -2. All right, now just working out what's in the square brackets. I see a lot of people forget to put the brackets or put parentheses around the 2×2 determinant, and then they wind up multiplying 1 minus lambda times 2 minus lambda times negative lambda, and then they get something that's completely wrong. Besides the fact they get themselves into algebraic trouble. So do remember that you need to finish the 2×2 determinant before you multiply in the 1 minus lambda, if you ever do, depending upon what it asks for. In this case, we're not even going to multiply by that. All right, so I have 1 minus lambda still left out front, then -2 lambda plus lambda squared plus 2. Let's rearrange the entries in the square brackets so they look a little more familiar. I now have lambda squared minus 2 lambda plus 2 in the what used to be square brackets. Okay, now, like we said before, our goal here is to factor, but because the lambda squared minus 2 lambda plus 2 doesn't factor, I'm going to need to use the quadratic formula just for it. Now, the 1 minus lambda is fine. In fact, I can already tell you that one of my lambda values is 1. The rest of the lambda values are going to come from the quadratic formula. lambda is going to equal 2 plus or minus the square root of 4 minus 4 times 1 times 2 all over 2. Working out what's under the square root, I get negative 4. Then because 4 is a perfect square, it can come out of the square root as a 2, and the square root of negative 1 is I, of course. So 2 plus and minus 2i over 2 becomes 1 plus and minus I. And that's because I distribute the 2 that's underneath in the denominator to both of the entries. All right, so I have 3 eigenvalues in this case. I have 1, and then I have 1 plus I and 1 minus I. Those are my 3 values. Okay, now if I wanted now to find the eigenvectors for lambda equal to 1 plus I, remember what I'm supposed to do is to find A minus lambda I. Well, because lambda now is 1 plus I need to subtract that from all the entries in the main diagonal. Doing a little bit of simplification there. Across the first row, I get negative I, 0, negative 1. The second row is 0, 1 minus I, and 2. And the third row is 0, negative 1, and negative 1 minus I. Okay, now the next thing I was supposed to do is to reduce that on the left with zeros on the right. So I make an augmented matrix with the A minus lambda I on the left and zeros on the right. Now luckily, I don't have to do this. Not in my class anyway, not in Math 1114. When you get into differential equations, which is coming up pretty soon for you, you will have to reduce this. You'll have to try to get a 1 in that first position, the 1, 1 position. So I would need to multiply by something across the first row that's going to give me a 1 where the negative I is. Now I'll save, all that sort of thing for the differential equations class you're about to take. What I wanted you to see, though, was that we will never really eliminate the complex values. And as a result, our eigenvectors, if I can get it out, will be also complex. Okay, so a complex eigenvalue leads to a complex eigenvector. All right, that was the conclusion of section 4.3 about complex eigenvalues and where they might come from. Hopefully you've seen that if you have A plus BI, you have to have A minus BI listed as an eigenvalue. If you have a complex eigenvalue, you're going to get a complex eigenvector. Also, the only way that you're going to get lambda equal to 0 is if the determinant of A is also equal to 0. So I hope you have some things to keep you busy for a while, and I hope you enjoy section 4.3.